So now we look at something called the bandpass filters, and we're going to see that really it's the addition of putting two filters together, high pass or low pass, to build a bandpass filter. So a high pass filter with a critical frequency of 2 kilohertz and a low pass filter of a critical frequency of 2.5 kilohertz are used to construct a bandpass filter. Assuming no loading effect, what's the bandwidth of the passband? So the bandwidth then is equal to the lower critical frequency minus the upper critical frequency. So when we do that, we have 2.5 kilohertz minus 2 kilohertz gives us a bandwidth of 500 hertz. So that's how we look at bandpass filters. A bandpass filter allows a certain band of frequencies to pass and attenuates or rejects all frequencies below and above the pass band. So if we look at the examples below, again, the block diagram and then the waveform of the upper and lower and our center frequency, the bandwidth of a bandpass filter is the range of frequencies for which the current and therefore the output voltage is equal to or greater than 70.7% of its value at the resonant frequency. So as we have just seen then, the bandwidth is abbreviated as the difference between the upper and the lower, where FC1 is the lower cutoff, FC2 is the upper cutoff. And so we can see that as depicted in the waveform. High pass, low pass filter. A combination then of low pass and high pass filters then can be used to form the bandpass filter as illustrated below. So if we put in series, gang together the two different types of filters, the low pass and the high pass, then we can form a bandpass filter. So if we look at the output then of the low pass curve and the high pass curve, and we see right there in the center is where our center frequency is, okay, or the critical frequency. On either side of that, then we have our critical frequency 1 and critical frequency 2 that forms the center frequency in this case. A high pass filter then with a, okay, this is one we've already seen. Then the critical frequency of 2 kHz low and critical frequency of 2 kHz high. So as we saw before, that gives us a bandwidth then of 500 hertz. So if we look at what a series resonant bandpass filter looks like, it's an RLC network. So we've got an inductor, a capacitor forming the series resonant portion, and then we take the output across the resistor. So a type of series resonant filter that we've just introduced here, as you've learned in chapter 17, the series resonant circuit has a minimum impedance and a maximum current at the resonant frequency. So most of the input voltage is dropped across the resistor then at the resonant frequency. Therefore, the output across the resistor has a bandpass characteristic with a maximum output at the frequency of resonance. The resonant frequency then is called, in this case, the center frequency. We use FC or F naught, either one is acceptable. The bandwidth is determined by the quality factor. There's that quality factor that you were questioning that seemed to have been glossed over. Well, here it is. We're putting it to use again. Of the circuit and the resonant frequency as discussed in chapter 17. Recall that the quality factor then is equal to the ratio of X sub L and R, where R is the resistance of the circuit. So a higher value of Q results in a smaller bandwidth. A lower value of Q causes a larger bandwidth. So we open up or collapse that curve higher and lower to form the narrower or wider bandwidth. A formula for the bandwidth then of a resonant circuit in terms of Q is stated in the following. So the ratio of the frequency by the Q gives us the bandwidth. So we've got another relationship that we can use to solve for several variables. So in this example, we want to determine the output voltage magnitude at that center frequency F naught and the bandwidth for the filter. So what we have here, let's take a look at this circuit. We've got a 1 millihenry inductor that has a winding resistance of 10 ohms. We've got a capacitor that's 0.0022 microfarads, okay, tens, hundreds, thousands, 22 thousandths of a microfarad, and a resistor on the output of 100 ohms. So at the center frequency, F naught, X sub C and X sub L are reactive components, cancel, and the impedance of the resonant frequency is equal to the winding resistance. So the total circuit resistance then comes down to just that tiny little RW, the winding resistance, and the resistor. So that relationship then can be handled by using, again, we go back to that voltage divider relationship that we learned last semester in 131, R load over the sum of R load and RW, the winding resistance, times the input voltage. So 100 ohms divided by 110, when we combine the two, divided by 10, gives us 9.09 volts. So now to calculate the center frequency. The center frequency is 1 over 2 pi, the square root of LC, which we saw early on back a couple chapters ago. We get 107 kilohertz as our center frequency. So at that center frequency F naught, the inductive reactance is, so we rely on our inductive reactance relationship, 2 pi FL. So 2 pi at that center frequency, 107 kHz times 1 millihenry gives us a reactive value of 672 ohms. The total resistance then is equal to R total, which is R sub L, the load resistor, and RW, the winding resistance in the inductor, of 110 ohms. Therefore, the circuit quality factor Q, X sub L by R total, comes out to the product, or the quotient, 672, 110, 6.11. The bandwidth then can be solved by using the center frequency, 107 kHz, divided by that Q, 6.11, or 17.5 kilohertz. So our bandwidth then for that circuit is 17.5 kilohertz. Okay, so that's just the example. We just saw the circuit. So when we come back, we'll take a look at then the parallel resonant version for calculating the bandwidth and center frequency.